Hello everybody, my name is Roseline. I am the product line manager of Knowles product at SELTECH. It's nice to see so many of you joining our virtual event. Let's start this webinar. Giulio, what is the plan of today?
Thanks, Roseline. Hi everyone. This afternoon we will have our partners and friends from Knowles. In this webinar you will learn about MEMS microphone technology from the global market leader and what its advantages are over alternate solutions. You will also understand the key specifications from the datasheets and which of these specifications are critical for different applications. We will now leave Paris to join the windy city of Chicago, where Knowles is based. So take a nice cup of coffee, relax, not too much, and enjoy this webinar and stay safe. Hi Raghav, thanks for taking the time to share your knowledge with us. The platform is yours. Bye.
Good morning, good afternoon. Hopefully you are in the US. This is Raghav from Knowles Electronics. I'm a product manager here for MEMS microphones. Hope you're having a good day so far. So today I will be covering a little bit about who we are, what does Knowles do, and then talk a little bit about what constitutes a MEMS microphone, what are the components of it, and then cover a little bit about the key specifications of a microphone and how to think about them as you are using them for your application. So a little bit about who we are. So Knowles was started back in 1946. And we were the inventor and creator of miniature products, microphones, as well as receivers for hearing aids. And for a long time, we were focused on the hearing aid market. Back in 2002, we started the MEMS microphone for consumer electronics. That was the first ever of its kind for the consumer business. And ever since, we have been the market leader in this space. So what do we offer to our customers? The way to think about it would be four key things. One is we offer scale. We have built about 20 billion microphones and shipped 20 billion microphones to date. In the last 20 years, we have 2 factories. We have multiple sources on our vendors. And again, the engineers who are listening to this may not want to hear it, but again, at the end of the day, the supply chain. There have been supply chain challenges in the world today. It's a crazy world we are living in, and in this unprecedented times, having multiple sources geographically different places helps, and that's the value of having two of these factories in different places. We also design our own MEMS ASIC and packaging. These are the key things that go into a MEMS microphone. We own entire R&D as well as we manufacture them. So do a full end-to-end design as well as manufacturing. So any questions specifically on any aspect of this, we are a one-stop shop. From a support standpoint, we believe we have one of the best supports in the industry. We have a very good network of partners like SELTECH, as well as our own field application engineering, as well as application engineering teams who are there to support our customers for any questions that they may have as they're integrating the microphones into their system. Last but not the least, from a quality standpoint, we believe we have a very strong value proposition. We are always talking about product robustness in our products. And we also have dedicated teams on the ground close to the factories where a lot of manufacturing is happening to ensure customers get any help and support they need during the manufacturing phase of the products. So again, market leader based on scale, technology, support, and quality. So with that, let me dive right into what constitutes a MEMS microphone. So MEMS stands for micro electromechanical system. It's a silicon-based mechanical motor that is implemented in the MEMS element, and we are can you guys hear me on the phone? Okay, sounds like we had some technical difficulties here. So we are talking again. MEMS microphone is constituents of MEMS, ASIC, and packaging. MEMS is the element that is collecting the acoustic energy, and think of MEMS like a mechanical motor, a very small motor with two discs. One of them is always moving. As the sound energy hits the disc, it moves, and this movement creates a change in capacitance. And this capacitance is getting picked up by the ASIC, and that is what gets translated into electrical signal, either analog or digital, depending on the interface of the microphone. Last but not the least is the packaging piece. The packaging is what covers the MEMS microphone and protects the MEMS element. Also, it provides the necessary volume, what we call as the back volume behind the MEMS, and this helps helps in terms of figuring out the SNR of the microphone. And I will remember these words, the back volume. I'll refer to these as I talk a little bit about the specifications of the microphones in subsequent slides. Okay, so moving on to what are some of the benefits of the MEMS microphone over other technologies. MEMS microphone is before MEMS came into the market in early 2000. ECM or electret condenser microphone was widely used. But there were some issues with that technology, and three key things that stand out for MEMS over ECM. One is ECMs were not very easy to surface mount, so a lot of manufacturing that happens today is automated place and pick and place process. ECM with their structure here, as you can see, there are three wires that are coming out of a cylinder, not very friendly from that manufacturing process perspective. MEMS, on the other hand, because of it's built on a PCB, it's much more reflow friendly. It can be automated manufacturing processes can be used to integrate that in the manufacturing side of the device. The second piece is technology and the stability of the technology. So ECMs often had issues with environmental stability, and MEMS, because MEMS is based on silicon, it's much more stable, and silicon is a much more stable material. So it provides the environmental stability and vibration, also against vibration shocks. Sensitivity of MEMS also does not shift over time compared to an ECM. ECM tends to shift a lot more, and so that they are not very conducive for things which require very stable sensors. Last but not the least is the power supply noise rejection. ECMs, because they typically have a two-wire interface, they have the output and the VDD line are coupled together. So any power supply perturbation really couples directly on the output of the microphone, which the MEMS microphone does not have this issue. So because of these problems, we started seeing a massive adoption of the MEMS microphone, and now MEMS microphone is used in about more than 95% of the applications in the world today. Okay, so now that we understand why MEMS came into folk and what are the key components of a MEMS, let me dive right into what are the key performance metrics or performance indicators of a MEMS microphone. And really, you can bucketize into three categories. One, acoustic performance. Second, electrical performance. And third, mechanicals. Um, Starting with the acoustic performance, we will talk a little bit about signal to noise ratio and total harmonic distortion acoustic overload points. These refer to the performance of the microphone. The electrical performance would be gauged by power or supply or current consumption of the microphone and the interface that we use, be it analog, be it digital, be it differential, single-ended, and so on. The mechanicals are we'll tackle, which are something that's slightly unique to microphone, the port location. Now, microphones do have an open acoustic porthole for the sound energy to come, for the sound to come in and hit the MEMS structure. So there is an open acoustic porthole, and depending on the location of this porthole, it can be a top port microphone or a bottom port microphone. And I'll explain a little bit of what it means and what considerations you can think about as you're integrating them in your devices. Last but certainly the most intuitive probably is the size. Again, this is a very clear function of what is the footprint that you're planning to have in your device and how sensitive it is to the size. So we have a variety of sizes in our portfolio. So that's hopefully the most intuitive part. But typically, care-abouts in a system design are these three buckets: acoustic, electrical, and mechanical. So let me start with the acoustic performance and talk a little bit about signal to noise ratio. So signal to noise ratio is often an indicator of the performance of the microphone. The technical definition is it's the ratio of the 1 kilohertz sensitivity to the A-weighted noise. But what is really telling us is what is effectively the mic self noise. And the way to think about the mic self noise is in relative to the environment that you're planning to use on. What is the microphone? What is the target microphone self noise? And what are the things that you're looking to capture? And is the self noise of the microphone above that sound pressure or below that sound pressure level? So to give you an idea of what that will look like, on the left side of the slide, you'll see a rough table that talks about the different sound pressure levels that you typically hear and associated with different sound patterns. If you have starting with the drill machine at the top, it's very loud, it's annoying, it can potentially make you deaf, 130 dB, to something very quiet like a recording studio or a broadcasting studio at a 20 to 30 dB range. So you have ambient noise that are or ambient sound that are in this range of signals, and depending on what you want to capture is what drives the thought process behind picking the microphone noise floor. So if, for example, if you were using a 60 dB SNR microphone, you would be only capturing your microphone noise floor will be around 34 dB, and you will be only capturing signals above that. You will not be capturing anything below that. So now that we have a 70 dB microphone in the portfolio that we see across the industry, the noise floor now drops by 10 dB, and you can start capturing a lot more, especially in quiet environments. You can start capturing a lot more sound, and that's one way to think about how to pick your SNR. Then the next thing to think about is really tied to which use case and which application you end up using the microphone. Now, typically what we see is, be it a single mic or a multi-mic applications, customers typically add a lot of gain on the output of the microphone. And this gain, unfortunately or fortunately, the gain also amplifies the noise that is coming in from the microphone. So it's not just that you're gaining up the signal, you're also gaining up the noise. And this is exactly where the microphone noise floor again plays a role, where you don't want to be hearing that hiss or that sound. One classic example that we have seen in the industry is a TWS headset, where microphones are used for ambient noise pickup. And when you're trying to pick up an ambient noise that is very, very quiet, in quiet condition, let's talk about a recording studio. Um, you're trying to capture that level of sound, and you are gaining up the microphone output significantly. And what tends to happen is if it's quiet, you tend to hear the hiss of the microphone noise floor. And that hiss is not a pleasant hiss, it's a very annoying sound, and consumers don't appreciate that. So typically that's where we see appreciation for using the very high SNR microphone, and this is something that we have seen take off in the industry. The other place that you will see a lot of high SNR microphone is also a ANC headset. And the reason is as follows. ANC is typically implemented as a mixture of feedback and feed forward, and I'll explain a little bit of what it means. So think about what ANC is trying to do. When you put on the headset, all it's trying to do is cancel the environmental noise around you, so you have a very quiet experience. And the way it does that is there is a outside facing or feed forward, as you can see in the picture here, FF microphone that is in the outside world that's picking up what's the sound outside the headset. And then the signal chain in the headset generates the anti-noise and feeds them back to the speaker. Then there's a microphone that is listening to the speaker output called the feedback microphone. And as it's listening to the speaker, it's feeding back to the signal chain to check if it is canceling all the noise or there is still some noise remaining. Now, if your feedback microphone is a very low SNR microphone, it will actually not capture some of the sound that you're hearing, and then you will start hearing hiss of the microphone noise floor itself as well. So this is where again, as you're designing these systems, you have to think about it from multiple levels on how complex the system is, and how using a sensor which is not a very high SNR can cause inadvertent effects in the implementation. So outside the ear market, we also see a growing demand for high SNR microphones in other markets. And really the use cases that drive it are typically recording use cases or far field use cases. So recording is used for mobile devices. Think about you're trying to record something that's slightly played at a distance, and you're trying to capture a high fidelity signal from it. A high SNR microphone, again, can help capture that without the background hiss. Think about a IoT device where you're trying to speak to an IoT device, and as you go farther and farther away from an IoT device, our speech signal falls exponentially with distance. So when if you're designing like something like a smart speaker, a very high-end smart speaker where you want the voice pickup from a far away distance, you would want a higher SNR microphone because you don't want the speech to be below the microphone SNR or microphone noise floor. Otherwise, it won't ever capture that sound. So again, depending on what you're looking to design, there are ways to think about the SNR. Hopefully, it gives you a flavor about how to design your TWS, mobile, or IoT device as you're thinking about mic SNR and using it in your application. So moving on from SNR is the next performance metric, which is called the total harmonic distortion or acoustic overload. So total harmonic distortion is essentially telling you how much distortion is in there in the microphone output for a given sound pressure level. What you would also see is these percentage points in the data sheet. You will see 1% harmonic distortion and 10% harmonic distortion, also called as acoustic overload point or AOP. And really, these are indicators to tell you at what sound pressure where the microphone output completely saturates. And when I say saturates, what you hear is a static at the other end. And an example, just to give intuition behind what it sounds like, if you're talking to somebody who is walking outside in windy conditions, if because of the wind tends to be a low frequency signal that saturates the microphone, the static that you hear on the other side, which is the unpleasant static, that is effectively the sound of the microphone getting saturated. So that is effectively what happens when your microphone is saturated. So even when in a recording use case, when your sound pressure is significantly higher than what the microphone is designed for or is capable of, then you'll start hearing distortion in the output, which is the sort of like the static that you hear in the wind case. And talking a little bit about what use cases are where this is relevant, there are a couple of places where we see a lot more relevance. So the way we think about it at Knowles is we look at the CDC website and we see what is the average sound pressure level in for different venues and different use cases. So here you'll see a snippet of reference of input signal where CDC says the typical average sound pressure level in entertainment venues, if you're recording concerts, that's about 105 to 110 dBSPL, and that's the average. The thing that tends to happen a lot is a lot of these concert music is not a very static music. There is a lot of peaks to it. And when I talk about peaks, I show an illustration here of a musical instrument that gives about between 50 to 20 dB of peak sounds. And so at that point, you start hitting the the saturation limit of the microphone. And so if you're having a microphone which you picked, let's say a 120 AOP microphone versus a 130 dB AOP microphone, you can immediately see a difference in the saturation level of the output. Here you can start seeing in the picture on the right, if you have a 120 dB AOP microphone, there's a lot of distortion because these peaks tend to saturate the microphone and you really don't capture any signal after that. And all you hear is the static. If you use a high AOP microphone, you override this problem and essentially have a very stable and distortion-free recording in that use case. So again, this is one of the ways, like you talk about concert music recording, but the other place that we see AOP being important is also ANC applications, especially in the inner mic. Where the sound pressure levels inside the ear can sometimes get very loud, especially if it's an occluded system. So again, considerations to keep in mind as you are designing a system where THT or AOP is important. Okay, moving on from acoustic performance to electrical performance, I'll talk a little bit about power. So power is in data sheets, you will see power written not directly as power, it will be shown as a current consumption in our data sheets. And intuitively, you might think, well, power is always important and you always want to keep the pick the microphone, which is the lowest power. But really the way to think about it is what is the right trade-off is to think about what application you're using the microphones in. So I have three buckets of applications that I'm showing here. One is the plugged-in device. The second is a device where we use a large battery. And third are devices where the battery sizes are significantly smaller. So for a plugged-in device, microphone power typically is not a big percentage of the overall power budget, and so typically does not end up mattering. For devices like smartphones and laptops, when you're using them in normal mode, for example, let's say when you're talking to somebody on their smartphone or doing recordings on smartphone, the microphone is running in fully normal power mode. In those cases, the microphone power budget relative to the overall system budget is significantly small. So it is not as important in when the phone is with the display being on and other components being on and the signal chain. It's relatively low percentage of the overall power budget. But the interesting cases start beginning when you have something like an always on use case for a smartphone. Let's say your smartphone you have enabled Hey Siri or OK Google on your smartphone, and you have a microphone that is always on, that's trying to listen in for the magic keyword before turning on the rest of the system. So in those cases, the overall power budget is significantly smaller, and that's when microphone power starts becoming interesting. The other place where microphone power starts becoming interesting is for the small battery devices, and here there are a couple of vectors that drive that. First is in the TWS device, for example, typical microphone count will be 4 to 6 microphones, and so you have a large count of microphones that's running. Here in low power mode, for always on use cases, maybe only one is on, but again, low power mode, current then starts mattering because your battery is very small, the capacity is pretty small, so the power budget is very low. Even in normal mode, if you think about if TWS has ENC in it and you have ENC turned on all the time, that a typical ENC implementations use between 4 to 6 microphones. And that itself then starts becoming a normal power mode of the microphone starts becoming important. And that is where the optimization comes in to pick the microphones based on power, because this is where it actually can make a tangible difference to the platform. So again, there are ways to think about it. The point of this is to hopefully give you a frame of reference as you're designing and integrating these microphones to how to go about the thought process about which parameters matter more. And hopefully you got a lens of how to think about the current, both in normal power mode and low power mode. Okay, moving on to the second electrical parameter or metric of concern, which this is the interface. And you would see microphones that are analog. In analog, you would see single-ended as well as differential microphones, as well as in digital, you will see PDM or I2S microphones. So there's there are options as if you think about analog and digital microphones. And really what you should choose is a function of, again, your system design. But the important things to keep in mind are as follows. If you're looking at an analog and a digital microphone, and if you're just looking at them in isolation, that is not the right way to think about it. The right way to think about it is think about the entire signal chain. The entire signal chain is effectively the same, independent if you use an analog microphone or digital microphone. If you use an analog microphone, as I'm showing here in the dark blue section, you still need an ADC, a discrete ADC, or an integrated ADC that converts an analog to digital. And so comparing, for example, power of analog microphone versus digital microphone is not a meaningful exercise because analog microphones does not have the ADC, but digital microphones do. So by default, by design, they're doing something more. They will consume more power. But the way to think and compare is if you have analog and ADC, add up the current values of the power values there to compare it to the digital microphone and see which one comes out ahead. The other consideration that goes in these conversations is also the SNR. Not exactly meaningful to compare a directly analog microphone SNR and digital microphone SNR. And that's because, again, it's a function of what ADC you choose. If you choose an ADC that is not very, let's just say let's say it's a low-end ADC whose noise floor is significantly higher than the microphone noise floor, then your analog mic implementation is really constrained by the ADC noise floor. So the way to think about that is always keep analog microphone plus ADC as a reference, and then compare it to what you're getting at the system level to additional microphones. What we have empirically seen is, unless you're designing, you're picking up the highest end codecs of the ADC, typically digital microphones tend to come out a little bit ahead in SNR compared to an analog plus ADC. And again, depending on the implementation, we see many a times digital microphones come out ahead. But if you use a very high-end codec, then there is a chance that you can come very close or match to what is being offered. So something to keep in mind as you're thinking about the interface. The other point I want to make here is also think about the number of microphones that you have. For example, if you have integrating 6 microphones, and you look at an analog microphone cost and you say, well, an analog microphone cost is let's say 30 cents, and I'm using 6 of them, so I got to pick the cheapest one. I cannot pick the more expensive digital microphones. But really, to keep one thing in mind is you will also be putting an ADC in front of it. So you have to add in the ADC cost and think about ADC cost plus the microphone cost, and does that come out ahead of what you're using in the digital microphones? We use 6 digital microphones, for example. And again, very implementation specific thing. So keep in mind these factors as you think about designing systems with analog or digital microphones. Okay, moving to the mechanical piece of it. Mechanically, we talked a little bit about microphones being slightly unique in the sense that they have an acoustic porthole. So depending on where the acoustic porthole lies relative to where the solder pads lie, you either have a bottom port microphone where the acoustic porthole is in the same PCB as where the solder pads lie, or a top port microphone where the acoustic porthole is on the opposite side of where the solder pads lie. And what to use when is a very mechanical ID-driven discussion or decision. But what we typically, from a microphone standpoint, what we typically can say is a bottom port SNR, a bottom port microphone, while it may add some challenges at the integration level by requiring a PCB with specific, a special PCB with a hole, the challenge that we, the advantage of a bottom port microphone is it has a higher back volume, which means that for a given footprint size between a top port and bottom port, you would end up seeing a higher SNR or higher performance out of a bottom port microphone compared to a top port microphone. So I think I referred a little bit about back volume in the past when I talked about packaging. So back volume is effectively this volume behind the MEMS, and this is what gives it a sufficient area for the MEMS to move and collect as much sound as possible. Versus if you think about a top port microphone here, the back volume is really very, very small, and the front volume, the volume behind and in front of the MEMS facing the porthole is significantly larger. So that makes it a challenge from a microphone designer to give an equivalent SNR in the same size package for a top port. Now, there are often packaging tricks that our R&D team has in their book to kind of maximize what SNR they can get. But again, if you're looking for, if your application can handle a bottom port, typically we see customers opting for bottom port because same packet size, tend to be slightly higher performance, tend to be slightly cheaper compared to our top port. Now, it doesn't mean top port has no future. There are places where top ports are needed, and we see them used in certain markets. But it's again a very ID-driven choice. Okay, so hopefully so far you've gotten a flavor of how you think about the microphones and different aspects of the microphone parameters as you're using them in your designs. I will jump in and quickly give a brief overview of the microphones that we offer. And really, this is not an exhaustive list. The full list is on our website. But again, all the things that I talked about in terms of the SNR, in terms of the THD and AOP performance, we rank our microphones which have the highest SNR, highest THD and AOP for a given size as the best in class microphone. And then from there on, the list goes down So here you'll see a 68.5 to a 64 dB, a wide portfolio of offering depending on all sorts of use cases that you can consider. And if you remember the chart that I showed on the SNR slide, depending on what you're looking to capture, so we have the full range of SNR as well as AOP on our portfolio that should be fairly versatile for any of your applications. Same thing on the analog microphone. You will see that there's a wide variety of performance, wide variety of form factors to be for depending on how your ID is getting designed and what kind of system you're designing and what kind of signal chain you're designing. The call out I do want to have is a couple of automotive microphones that we launched recently. We have one analog and one digital. Again, these are slightly different than the consumer ones. You will see that these are coming in with AEC-Q 100-103 qualification, which is the standard now for automotive microphones. You will also see that they have a special variant that can come in with a tightly matched plus minus half a dB tightly matched sensitivity, which customers often need, especially if they're facing a margin stacking problem on their manufacturing, and they would prefer a tighter distribution coming in from the sensor so they can manage their margins on the manufacturing better. So again, a lot of variety here. Please reach out to your SELTECH representative or Knowles representative if you're interested in any of these. With that, I will conclude my presentation for today. Hopefully, what you have learned today is what are the things that constitute a MEMS microphone, and learned about how to think about SNR, AOP, power, and the mechanicals as you're using them in your applications. And again, this sounds cliche, but I mean, all specs are important. But again, depending on how you're using them and what use case you're using them, some may matter more than other. So something to keep in mind as you're going about it. At this point, if you have questions, I would like to open it up. And again, this is hopefully this was useful. If you have ideas of things that that you want to learn more about, if I can't cover them in the Q&A, please let us know. Happy to have subsequent webinars cover those topics.